So it's my pleasure to introduce Plinio Murillo, and he'll tell us today about the kissing number of hyperbolic manifolds. The floor is yours.
Hello, thank you very much for the introduction. We'd like to thank the organizer for the opportunity to speak in this very nice conference. I have been able to be with you from here, and so it's I also thanks the technology that allows us to connect nowadays. Okay, let me see if it goes. Okay, I will talk, as I mentioned, as it's written in the title. I will talk about the kissing number of some hyperbolic manifolds. And I have to say that this is a joint work with two collaborators, Brazilian collaborators, Caio Doria and Emmanuel Freire. Okay, so let me start with the players of this story. So the systole, you saw in the beginning of the week in Benjamin's Dinovis talk, this notion of systole. So he defined it as the length of a shortest geodesic in a Riemannian manifold in general. So I will change a bit. So for me in this talk, the systole will be the not just the length, but the closed geodesic itself. And this is a closed geodesic that realize the shortest length. So as we saw in Ben's talk, when he made some historical remarks, and it's very nice. So I can just go directly to what I want to talk. And the kissing number is nothing but the number of systems that we can have. In general, it's some Riemannian manifold, but I will restrict basically to hyperbolic manifolds. So we have these two concepts, systoles and the kissing number. And as it also was mentioned in Ben's talk, when we have this geometrical invariance, it's very interesting trying to relate this to other geometrical invariance. So this is what I want to talk. So we saw in Ben's talk that there are some relation of the systole with the volume. So what I want to talk today is about the kissing number as some relations with the volume. This is basically what one of the goals of my talk. So these relations started appearing in 2013 with the results by Hugo Parlier. So Parlier managed to relate the kissing number of a hyperbolic surface, a closed hyperbolic surface, in terms of the area. So we found an upper bound. Let's say some constant times the area square over logarithm of the area of the surface. And if we think that if the area is very big, we can think that this upper bound is about area power 2 minus epsilon for any epsilon. I mean, I'm thinking that the area really grows. So a bit later, 2015, Hugo Parlier, again with Federico Fanoni, they generalized the results for hyperbolic surfaces with cups. So he proved something very similar, that in this case, the kissing number of the surface is bounded about by some constant times the genus plus the number of costs times the genus over logarithm of the genus plus 1. Again, C is a constant that we are not very interested here. But the bound is quite similar to what happens in a closed case. And more generally, in 2022, Maxime Burke and Bram Petri, they realized this, they generalized the result to general hyperbolic manifolds in many dimensions in the closed case. And they proved that the kissing number is bounded about by some constant times the square of the volume of logarithm of 1 plus the volume. And again, if we think that if we are dealing with manifolds with large volume, you can think that this goes like volume power 2 minus epsilon. So this power actually doesn't change, so it doesn't depend on the dimension. I would think that the volume is very large. This article was published in 2022, but the preprint appeared in arXiv actually in 2019. And this is important because, well, it was in 2019 that it was called by Caio. And he has some question when he knew about this paper. So he asked whether there are hyperbolic manifolds with a large number of systems. So in this result, we only have an upper bound of the number of systems, but it can happen that the Kissing number is very small. So in the beginning, there is no reason to say that this number is comparable with this bound. And a bit more, it's possible to attain the upper bound in Burki and Petri result. It's and this is what for us large means. So either we want to really attain the upper bound in the previous result, or we can or we want some manifold with as many systems as possible. So, and you see, you will remind here that the upper bound is volume power 2 minus epsilon. So this is what we are trying to look like some hyperbolic manifolds with the number of systems, something like volume power square minus epsilon. This would be the best. Okay, so we started working in this project. And the first thing that we did was to look at the bibliography and well, what was known at the time. And this was also a reason to work in this. In 1987, it was proven by Schmutz-Schaller that if P is a prime number, an integer, it's a prime number, but it's sufficiently large, then the number of systems of this quotient that you already saw in Benjamin's Linovic's talk, this is as a congruence cover of the modular surface, actually. So the number of systems of this surface is at least the area of the surface power 4 over 3 minus epsilon, if P is very large. So more concretely, just to remember, this congruent subgroup is just take the modular group and take the kernel of the modulo P map. So you reduce modulo P, you just take the kernel of this map. And this was actually, as I mentioned, this already appeared at the beginning of this week in the conference. And he has proved that you can change the group. So it's not only for the modular group, but for any uniform arithmetic function group defined over Q, there are some congruent subgroups of this function group that the same happens. And the point here is that all the arithmetic groups that he considers are defined over Q. And this is this kind of spaces are the Buser-Sagnac spaces that appear in the beginning of this week in the event talk. And yeah, this is the congruence, let's say the easiest congruence subgroup that we can start work with. So this was already proven by Schmutz in 97, but nothing else was known. So what I tried to do was, of course, try to generalize this to higher dimensions. This was our attempt. Remember that we knew how the systole grows and the systolic length grows. So not just we wanted to measure the amounts of systoles, but we knew how to deal with the systolic length of the length of a systole. We had some previous work done on that. So we wanted to generalize this in this case. So the result that I wanted to communicate today is the following. So fix dimension, any dimension, and bigger than 2. So what we managed to prove is that any arithmetic hyperbolic n manifold of the first type defined over a real quadratic number field. So it's not over Q, but over a real quadratic number field, has a sequence of congruence covariance with the volumes going to infinity, and the number of systoles grows at least as a constant times the volume power 1 plus 1 over 3n n plus 1 minus epsilon. And here is for any epsilon, and where n c is a constant. So we don't worry very much about these constants. So we have something good, and we have something that maybe is not that's good. The good point here is that, okay, we get manifolds in any dimension with many systems, so we managed to produce these examples. But we wanted something very close to 2 in this power. And as you see here, once the dimension grows, this just decreases. So we are getting further and further that we wanted at the beginning. So it's just we are far from 2. But okay, this is what we got. And well, this is what it is. So I just want to share with you some ideas in that we learned when we were working this.
For you.
Sorry?
We have a question for you. 1 second.
Oh, yeah.
So this result does not recover the previous one when n equals 2 because number is different.
Say again? Sorry.
Does your result recover the previous result for the n equals 2?
It's a nice question. Well, when it's equal to, this is not the same. So this is worse than dimension 2 is worse. So the idea we try to generalize the smooth method, but to go to higher dimension, the computation gets more tricky to fix altogether. So we have to just admit that we couldn't do it so much in dimension 2, but well, and it's just worse, but at least it works for any dimension. And I will, if I have some time at the end, I will comment a little bit at the end, because this in dimension 3 we also managed to do a bit better than that, but particularly for dimension 3. And why basically and Alan Reed mentioned in this week too, that when we are dealing with 2x2 matrices, things are getting much easier. So basically, this is what is behind. So once we go to higher dimension, to control some things, it's much more difficult.
Thank you very much.
Welcome. Any other question? Okay. So let me just share some ideas. Just very quickly, remember that for any dimension, this arithmetic hyperbolic manifolds of the first type can be constructed in the following way. I just wrote a very specific way to do it. So we have a totally real number field. We consider a quadratic form of dimension n plus 1. That basically, when you conjugate, but the Galois embeddings of the number field, you get a positive definite, or it doesn't need to be positive, but it need to be definite. So for taking a very particular construction, you take a quadratic form like that. Minus is 0, it's x0, which is 0 squared, plus 1, a1, which is 1 squared, plus an, which is n squared, where all the coefficients are 1 or 2, are 0 or 1, a1, a2, and an are positive, and they lies in the ring of integers of the number field. But when you conjugate the coefficients with the Galois embeddings of the number field, so you get this quadratic form definite. So in this case, it's positive definite. So you take gamma being the integer points of the spin group defined by f. So just to recall briefly, the spin group is the universal cover of the orthogonal group defined by in the algebraic sense. And you take the modulo, the kernel of the modulo I map that is just you apply the modulo I map to the entries of gamma, and you just take the kernel, and I is some ideal, any ideal of the ring of integers. So I'm doing very quickly, but this is basically what we do for the modular group, just more imaginary. So we obtain what we call a congruence covering map. This is a covering map between this manifold. This is usually a manifold, and M can be, it's usually an orbifold, but this is not a problem for that because we are dealing with these spaces. So what we like to do is, what we like to say is that these manifolds Mi, they have large number of systoles. This is what we like to say. And why? Because basically this is what Smuts did for the modular group. So okay, if it will work, it will be nice, but well, this is what we like to say. But it's difficult to say so in this case, because how can we detect the systole of Mi? It's not easy to detect in general the systoles, and we are not able to know how many systoles this Mi has, and it can has only one, for example, only two, like a very short number. So how can we guarantee that this has many systoles? This, even if this is the idea, and in dimension 2 for arithmetic groups from Rapinchuk it works. When you go more generally, it's these two problems particularly appear. So this is part of what we had to overcome. So how can we just how can we overcame this problem? So look at the I will just mention the idea. I think it's a nice idea. It's very simple, but I think it's nice. Look at this quadratic form. This defines some manifold, an n manifold, but inside of that we have this part. And if you do exactly the same construction, what you get is a surface. So you have a surface inside your manifold. And surfaces somehow can be much easier to deal with. So we were thinking how to use this to match and try to say that Mi has a large number of systoles. So basically, this is what we try to do. So and this Si that is defined by just this piece of the quadratic form, it defines a totally geodesic surface embedded in Mi for any idea. So we can repeat the construction and we can construct this embedding. And if this is a surface and this is an n manifold, and it's of course true that if Si has many systoles, right? And every systole of Si is also a systole of Mi, well, this is clear that Mi will also have many systoles because we have at least the systoles of Si. So it was a very simple idea, but to put it in action and technically it's not easy. To put this to work is not easy because, well, this is not true in general, but what we did was trying to, even with that, modify the surfaces I and the manifold Mi to go to finely shifted coverings and keep the same the same totally geodesic embedding. I mean, like the same situation that satisfy these two conditions, that we have a surface inside the manifold, and we can guarantee that the surface has many systoles, and any systole of the surface is also a systole of the bigger manifold. And we managed to do that only for the case when K is a quadratic, as a totally real quadratic number field. This is basically the strategy, the technicalities. Well, we have to work a bit of that or a lot. But the geometrical idea is that try to generalize the method by smooths. Just a last comment, we also managed, as we mentioned before, we also managed to do a bit better in dimension 3. So we also proved that any arithmetic hyperbolic 3 manifold defined over an imaginary quadratic number field for any of those. This is a sequence of congruence coverings, Mi of M, with volumes goes to infinity, such that the number of systole is at least a constant times the volume power 4/3 minus epsilon. So we can improve a bit in dimension 3, and this is the same 4/3 that appears in dimension 2. This is a interesting curiosity. So we don't know how can be done better in higher dimension, but I am almost sure that the constant in higher dimension that we obtain is not the best possible. So there is a room to do better. So okay, thank you very much.
Any questions for Plinio? Yes.
So for a, let's say, generic manifold, you expect the kissing number to be 1, I guess?
Yeah. And actually, I didn't say that, but it was in the some papers said that, and they attribute this to some results of Anosov, but yes, yeah, it's for generic ones. It's one to be one.
So what would you say is like the motivation of this invariant? Like, does it have any geometric or arithmetic importance besides just being an invariant?
Say again, sorry, I don't know if I get that.
Is there any geometric or arithmetic importance for this kissing number invariant?
Well, I think this your comment and somehow answer this, because we are showing that the geometry of these arithmetic manifolds, it's very special, because it's very far from what the generic case is. So I see that I see in that way that the geometry of this is very particular, and it's very, for me, it's very in the direction that Larry Wolf, the comment that Ben said in his talk. Larry Wolf said that these are quite particularly somehow. So I think this result can be interpreted also in that way.
So do you expect that high kissing number should imply arithmeticity or something like that? Or?
That's, I didn't think about that, but I don't know. It's a bit strong. So I don't know, but who knows? Maybe.
Thank you.
It's interesting. Very interesting.
There's one more question.
So you said you get in dimension 2 and 3, you get a better estimate using a special expression of the spin group, right? But can you
dimension? Sorry, yes, please.
Can you get a similar result for, say, 5-dimensional case using a quaternions algebras? Like spin 1, 5, I think is SL2H, and like, I don't know, some quaternion algebra over number field. And can you get a similar better estimate?
What do you mean, like quaternionic hyperbolic spaces, or?
Yeah. I don't know. I mean, I think so you take an advantage that in the case of hyperbolic 2 manifold and 3 manifold, you use the fact that the spin 1, 2 and spin 1, 3 is identified with SL2R and SL2C or something like that, right? Is it correct?
Yes. Yes, but we also use a little bit the point, I think, yeah, it's also because we are dealing with quaternion algebras, but you see here In this case, we deal in dimension 3. We only managed to do for imaginary quadratic fields, and in the previous that for real quadratic fields. So I think that the most important so far is that the field of definition is quadratic.
Yeah,
and basically what is going when you go into details, the point is the following. When you have the length of the geodesic, you have to deal with two things. You have the length, but you also have some rotational angle, right? So, and in dimension 2, you don't have the angle, but in dimension 3, you only have one angle to deal with. You go to higher dimension and you and any loxodromic element, you have this the length of the aging values, right? The norm, but you have to deal with much more angles. And this appear that we have to control these angles. And basically we only managed to do that for quadratic fields because we only had one angle to take care of it. So we could manage if something like messy happened with the angle. So
dimension,
we are not able,
even when dimension is 5 or like that.
Yeah, I think that in the details this will be a problem because you need to control how you need to detect the systoles, and you need to really say which are the systoles. And to construct a manifold that you are sure that those are the systoles, you need to control how the angles behave. And this is something that we didn't manage to do in general. So we just manage when you have one angle.
Thank you very much.
Welcome.
Hi, Plinio.
Hello, Ben.
So a real quick question. For the modular curve, so in the classical case, I think lengths of geodesics correspond to something like regulators of real quadratic fields, and their multiplicities correspond to class numbers. Are there relationships with your kissing numbers and class numbers of certain extensions?
Yes, exactly, and that's the point. In dimension 2, this is what the smooths did. So the kissing number in this construction is exactly the class number of certain binary quadratic forms. So in this kissing numbers thing, the number of geodesic is basically a class number, and this is part of the problem because class number is not that easy to understand, right? So it's we know something with the class number and regulator, the products, but class number is something that we cannot control very much. And actually, yes, in dimension 2, this is 2, and dimension 3, we did that, and this relation also appears. So you change the modular surface by the Bianchi orbifolds. So in the Bianchi orbifolds in 3 dimensions, the number of closed geodesics in these coverings corresponds to the class numbers of binary quadratic forms over the ring of integers of some quadratic extension of the base field of the orbifold. So this really appears in this. I think it's beautiful because this geometric and this algebraic counterpart appears, and this is only so far in dimension 2 and 3. We don't know how it can be appear in higher dimension. I have no idea, but class numbers should appear, and it will be, of course, very at least for me, very interesting. It's sometimes I think that well, maybe we have to think about more general quadratic forms. I don't know exactly what is the algebraic object to try to compute this this class number to say that in higher dimension it does so much. But yes, of course, yeah, this is really something very interesting.
Thanks a lot, Plinio. In the interest of time, I'm gonna cut the questions short. Let's thank the speaker again.
Thank you. Thank you very much.
Thank you for joining at 4 a.m. I guess it's now. I can probably go to sleep.
Yes, it's 4:23 here. Yes.
Thank you so
It's
much.
okay. I slept a bit before, so it's okay. Thank you for the
Thank you.
opportunity and for the conference, the organization of the conference. Very nice.